Okay, so hello, welcome everybody to this session about model predictive control. I am Antonello Giannitrapani from the University of Siena, and I will be the chairman of this session. So we have 6 talks scheduled in this session, and we have almost all the speakers that are already here connected. And I remind you that each presentation should be 15 minutes long, more or less, plus 5 minutes for questions and answers at the end. For those of you in the audience and for all the attendees that want to make questions at the end of a presentation, you can simply write in the chat that you are interested in making a question, and the technician will allow you to speak. Okay, so I think we can start with the first talk, which is titled Multi-trajectory model predictive control, and this presentation will be given by Danilo Saccani. Danilo, please share your screen and start when you're ready.
Thank you for the introduction, and good morning, everyone. My name is Danilo Saccani, and I'm a PhD candidate at Politecnico di Milano. Today, I present my research work titled Multi-trajectory model predictive control, which was done under the guidance of Professor Lorenzo Fagiano, and that introduced a novel MPC formulation where multiple state trajectories are considered in the same finite horizon control problem. Let's start with a brief introduction and some motivations behind our work. In recent years, broad attention has been paid on autonomous systems due to their high impact on many areas of science, technology, and society. These systems, such as autonomous vehicle or mobile robots, belong to the spectrum of safety-critical applications. For this kind of applications, the guarantee of a safe motion and collision avoidance while their autonomous task is accomplished in an unknown environment are critical requirements. So we can identify 3 pillars: safety, so the need of guarantee a safe motion; the exploitation, so the need of carry out the autonomous task; and exploration, so the need of gathering information about the environment. Those requirements, however, are often conflicting, and our works aims at managing these conflicting goals, and in particular exploitation and safety, with a novel MPC formulation that allows one to partially decouple the constraint satisfaction, so the safety requirement, from the cost function minimization, so the exploitation requirement. Let's see first the main idea behind our work with a simple example, and then the generic formulation of this multi-trajectory MPC. So let's imagine to drive your car and approach a crossroad where there is a blinking traffic light. What we usually do is adjust the velocity of our car in order to be able to cross the crossroad as fast as possible, but also considering the possibility to stop the car if the crossing becomes dangerous. So the intuitive idea behind our work is to predict 2 different trajectories with a first common waypoint, this waypoint that represents the choice at the next time step. So we have one trajectory that is used to carry out the main task, so in this case to drive the car over the crossroad, and a second trajectory that is used instead to guarantee the existence of a safe maneuver, so in this case be able to stop the car before the traffic light. Let's see better the approach with its mathematical formulation. So let's consider a nonlinear discrete time system x of k plus 1 equal to f of x of k u of k, where x of k denotes the state time k, and u of k is the control action. Furthermore, for the control problem, we consider state and input constraints. So we have that the state x of k must belong to the set capital X, and the control action u of k must belong to the set capital U. Now, considering a prediction horizon, we can define 2 different input sequences. Note that the first element of for both the sequences is the same and is the one applied to the system in a receding horizon fashion. Now, starting from a generic initial condition, x of k, and feeding the system with the two input sequences that we have defined before, we can predict two different state trajectories named capital X first and capital X second. Note that, of course, both these trajectories shares the first state. Finally, we collect all the control action that we have used to compute those trajectories in a decision variable vector, capital U. Let's see now the finite horizon control problem solved at each time step. The goal of the control problem is to minimize a cost function j with respect to the decision variable vector u. And let's consider a tracking cost function, so a cost function that measures the distance between a state trajectory from a desired target x of t. As can be noticed, in this approach, we have two state trajectories, but only the trajectory capital X first is considered in the cost function. Let's move now to the problem constraints. So first of all, we impose the dynamics of the system to the two trajectories. Then we have the input constraints. So we have that all the control action used are subject to input constraints. And finally, we have the state constraints. In this case, we force only the second trajectory, so the trajectory capital X second, to belong to the feasible set. And as usual in MPC, we force the terminal state of the second trajectory to belong to a terminal set. So from this optimization problem can be easily noticed how we have partially decoupled the constraint satisfaction from the cost function minimization. Indeed, the first state trajectory is weighted in the cost function. Instead, the other one does not affect the cost function, but satisfy the state constraints. Let's see now better the approach with a case study. The algorithm has been applied to compute the optimal trajectory for the autonomous navigation of an unmanned aerial vehicle in an unknown environment. The goal is to navigate the drone to a target while avoiding a priori unknown obstacles. The drone is equipped with a two-dimensional LiDAR sensor, and the navigation must be performed by relying only on real-time LiDAR measurements. So no previous knowledge of the environment is assumed, and only real-time data are available. In this case study, the multi-trajectory model predictive control has been used as an high-level controller in a hierarchical structure. So at each time step, the controller receives as feedback the position and the velocity of the drone that is assumed to be exactly known, together with the LiDAR measurements, and provides the waypoints to a low-level position controller that acts on the nonlinear dynamics of the drone. To limit the computational burden and to use a linear time varying MPC, we have considered a linear model and linear constraints. As for the model, the closed-loop dynamics of the vehicle and the low-level position controller of the drone has been considered as a double integrator, where the position and the velocity of the drone are the state of the system, and the acceleration is the input. Then this linear continuous time system is converted to a discrete time with a sampling time of 1 second. As for the input constraints, instead, the acceleration is bounded by its minimum and maximum achievable value. As for the constraints, instead of the position of the drone, the environment is continuously scanned with a LiDAR sensor that provides a cloud of points describing the surrounding obstacles. So these LiDAR readings generates a non-convex region representing the free space. And in order to obtain linear constraints, we have developed an algorithm to under-approximate the feasible space with a convex polytope. The algorithm works as shown in the animation. So firstly, a regular polygon is built where the vertices of the polygon are placed at a distance from the drone equal to the minimum distance from the nearest obstacle. Then the vertices of the polytope are iteratively expanded, and at each iteration, if the expansion of one of these vertices includes 1 lidar readings, the vertices are blocked. So at each time step, a new convex polytope is built and is used as state constraints in the control problem, leading to time varying constraints. Finally, note that since no information are provided outside the plane of the vehicle, since only a 2-dimensional lidar is considered, the obstacles are assumed to have an infinite height. So at each time step, considering a linear model and linear constraints, we solve a quadratic programming problem. The resulting control problem so computes the optimal control action, considering one state trajectory, the trajectory x first, that is used to minimize the tracking cost function. So we can say that this trajectory is an exploitation trajectory that drives the state to the desired target. At the same time, is considered a second trajectory, capital X second, that operates inside the feasible set and tests its terminal state forced to be a stationary state. So in other words, we can consider this trajectory a safe trajectory that guarantee the existence of a maneuver in the obstacle-free area able to stop the vehicle before any collision occurs. However, due to the time-varying nature of the state constraints, a problem arises since the recursive feasibility is not guaranteed with standard MPC formulation. A standard practice to ensure the recursive feasibility is the use of a slack variable to soften the obstacle avoidance constraints. However, this approach allows the predicted trajectory to violate, if needed, the state constraints. That in this context of safety critical applications means allowing the predicted trajectory to collide with an obstacle. So in this work, we implemented an approach to still obtain the recursive feasibility, but without softening the obstacle avoidance constraints and without assuming any prior knowledge about the future evolution of the constraints. The solution is quite straightforward. Indeed, if the MPC problem at the current time step results unfeasible, the last set of state constraints leading to a feasible problem is used. Indeed, in this case study, the state constraints computed at the previous time step still represents a free area. And the safe trajectory, so the trajectory x second computed at the previous time step, still represent a feasible trajectory for the subsequent step. Note that, of course, this approach is valid only when a known but static obstacle are considered. Let's see now a simulation where the environment composed of randomly placed 3-dimensional obstacle has been considered. The drone has to cross the workspace to reach the target, represented as a red star in the top right corner. As can be seen, at each time step, a convex polytope representing the free area is built inside the lidar field of view that is represented by some blue dots. In the simulation, the two trajectories can be easily distinguished, and in particular, we have the red one that is the trajectory x second constrained to remain inside the polytope and to stop the drone inside this free region. Instead, the other one, the blue trajectory, is the trajectory x first that can violate the state constraints to drive the drone to the target. Finally, a comparison with a standard MPC formulation has been realized. As can be seen from the formulation of a standard MPC on the right, we have used the same cost function and the same state constraints applied to a single trajectory MPC. To perform the comparison, the simulation has been repeated 100 times, and 3 performance indices has been considered: the average target tracking error, the time to reach the target, and the computational time needed to solve the problem. As can be noticed from the table, where the results has been normalized with respect to the single trajectory MPC, the multi-trajectory MPC has a higher computational cost due to the increased number of optimization variables, but it shows a performance improvement both in terms of time to reach the target and in average target tracking error. So let me summarize. We proposed an MPC formulation to partially decouple constraint satisfaction from cost function minimization. This approach is based on the use of different state trajectories in the same finite horizon control problem, and has been applied to simulate the navigation of an unmanned aerial vehicle in an unknown environment. A comparison with a standard MPC formulation showed the good performance potential of the approach, and the use of linear model and linear constraints showed to be computationally efficient despite the increased number of optimization variables. Finally, some future works will be a deeper investigation on theoretical convergence guarantees of the proposed approach, the test on real systems, and the extension of this work to consider dynamic obstacles and nonlinear systems. So I want to thank you for your attention, and I'll be happy to answer your questions.
Okay, thank you, Danilo, for your very nice presentation. And I remind the audience that if they are interested in making a question, they can book in the chat. They can simply write in the chat that they want to make a question. In the meantime, I have a curiosity and probably a question. So first thing is, I'm not sure, probably I missed this, but when you use the LiDAR for building the free space around the drone, okay, so use that polytopic approximation.
Yes.
Are you then storing this information for future use? I mean, are you building a map, or are you just starting from scratch and you just are you just interested in the local free space?
Yes, of course. No, in this application, I don't store nothing, but of course, the convex polytope can be stored and can be used to build a map of the environment and to create a non-convex region by means of more convex under approximation of the free space. In this approach, is not considered at each time step. A new convex polytope is built and is used.
Okay. And something about if you have some stability proof of the overall approach.
As said in the conclusion, no, we are still investigating the theoretical convergence of guarantees of the approach, but of course the recursive feasibility is forced in with this strategy. But no, for now we haven't theoretical convergence guarantees.
Okay, thank you very much. I don't know if there is any question. I don't think so. Okay, so I thank you again. And in the meantime, I invite the second speaker, who is Mengjia, to share her desktop, her screen. Thank you, Danilo.
Thank you.
So that we can start. We have to wait 1 minute more to be on time. Okay, so I see you. Hello.
Hello.
Okay, just one minute and then we start. Okay. Okay, so you can share your desktop if you want. I'm not seeing it anymore.
Thanks. Okay.
Okay, now that's okay. Okay, so next talk will be given by Mengjia, and it is titled The Preference-Based MPC Calibration. So you can start when you're ready.
Okay, thanks for the introduction, and good morning, everyone, and thanks for attending this workshop. And it's my pleasure to share this work with you today. The topic is based on is the preference-based MPC calibration, and this work is supervised by Professor Bemporad and Professor Piga. Here is a brief outline of the talk. First of all, I would like to give a brief introduction of the calibration problem and the process, as well as our motivations. Then I will give a formulation of the MPC system and the tuning parameters. Following that, I will introduce a preference-based tuning method. And lastly, a case study of autonomous driving vehicle will be discussed and some conclusions will be drawn. So calibration is a common process required in control, and an example of closed loop calibration process is illustrated in this figure. The goal is to find the best control parameters. And here, the best can be interpreted as to find the control parameters that maximize performance objectives. As an example, for vehicle control, the objectives could be the objective could be to enhance the driving quality and reduce fuel consumption and etc. Human assessment is often involved. Calibration can be a very time-consuming and expensive iterative process. So 3 tuning methods are often used, which are manual, automatic, and semi-automatic tuning. For the manual tuning, both parameter adjustment and parameter assessment are done by human based on their intuition, expertise, and judgments. While for the automatic tuning, parameters adjust automatically by a computer based on a well-defined objective function. On the other hand, for the semi-automatic tuning, computers adjusted parameters based on human judgment. And this is approach that we explored in this work. So in multi-criteria decision-making, such as in control system design, it is often difficult or sometimes impossible to quantify an overall objective function for auto-tuning. Also, for fully manual operations, it can be very labor-intense, time-consuming, and costly. Therefore, an approach that balances between manual and automatic tuning is desired for such applications, which lead to the semi-automatic calibration for these applications. I want to discuss the main idea of our approach. It utilizes experts' knowledge and optimization algorithm. And the algorithm used is the active preference learning algorithm that I will discuss in more detail later in this presentation. And here are some key features of this approach. First, calibrator is only asked to compare the performance of pairs of closed-loop experiments and express a preference. Second, the algorithm GLISP is used to automatically propose the next comparison to make based on the expressed preferences. Third, quantitative scoring objective function is not required in this case. And also qualitative assessment of closed-loop performance is possible by using this approach. And lastly, near optimal performance can be achieved within a limited number of experiments. The approach is applied to MPC system, and our goal is to control a nonlinear multi-input, multi-output system as shown here. First, we apply a linear MPC strategy with constant sampling time to the system. And at each time at each sampling time t, we compute the MPC action by solving the QP system here, subject to their constraints. And several tuning parameters are presented in this MPC problem, such as the prediction and the control horizon, the positive semi-definite weight matrices, and also the tolerance used in the QP algorithm for solving the previous QP problem. In this calibration task, we assume that the closed loop performance objective function, which is also known as the latent function, is not available. And we can only express a preferences between two choices, theta1 and theta2, and the function form of pi is used. Here, if theta1 is better than theta2, which also implies that the underlying f of theta1 is smaller than f theta2, then we assign pi as -1. And if theta1 is as good as theta2, we assign as 0. And if theta2 is better than theta1, we assign it as 1. So our goal is to find a global optimum theta star that is better than any other theta. Mathematically speaking, we want to find a theta star such that pi of theta star of relative to any other theta that tested is smaller or equal to 0. So in the following slides, I will give a brief introduction to the active preference learning algorithm, GLISP, and it is developed by Professor Bemporad and Piga. And for more information and the code, you can visit this website. So first, we fit a surrogate function that respect the preferences expressed by the decision maker at the sampled point. Then we minimize an acquisition function to get a new sample theta n plus 1 by trading off the exploration and the exploration. Lastly, we compare the performance of theta n plus 1 to the current best point and then iterate. So here is a summary of the main procedures for the preference-based tuning. In this case, the latent function is the calibrator's conscious or unconscious score function in the mind. So the active preference learning algorithm GLISP proposes a new combination theta n plus 1 of the parameter to test. By observing test result, the calibrator expresses a preference telling if theta n plus 1 is better, similar, or worse than current best combination. Then the preference learning algorithm updates the surrogate of the latent function, optimizes the acquisition, and iterates. The procedure repeats until the maximum number of experiments allowed is reached. So here, the preference-based tuning algorithm is tested on an autonomous driving vehicle case study. The test scenario is illustrated here. So the controlled car starts at a position 0, 0 with a steering angle equal to 0 radius, and the obstacle car is 30 meters horizontally apart and moving at a constant speed of 40 kilometers per hour with a constant steering angle at 0 radius. So both vehicle is assumed to be a simplified rectangular shape with this dimension. So at the nominal lane keeping condition, the controlled car is moving at 50 kilometers per hour. But when the obstacle car is within safety distance, which in this case is set to 10 meters, the controlled car needs to overtake the obstacle car in an optimal way, and the vertical distance between the two cars needs to be at least 3 meters. And these are some constraints that apply to the velocity and the steering angle during the test scenario. So there are two main control objectives in this case, which are lane keeping and obstacle avoidance. Why use preference-based tuning in this case? So first of all, this task is a multi-objective calibration task. Also, for this specific task, it's very difficult to define a very proper quantitative scoring function in advance. For instance, it's hard to transfer the optimal obstacle avoidance into a mathematical formula. So for a simplified 2 degree of freedom bicycle model with the front wheel as the reference point is used to describe the dynamic behaviors of the system as shown here. And 5 tuning parameters is used in this test scenario, which are the sampling time, prediction horizon, the fraction epsilon c between control and the prediction horizon, as well as the entries for the weight matrices of manipulative variable Q delta U. So these are the criteria that are used to assess the closed loop performance of experiments. The first priority is that the computational time of the QP in the MPC needs to be smaller than the sampling time. Then during the link keeping phase, the control car needs to move at a constant speed with vertical position and the steering angle close to 0 meters and 0 degrees. And during the obstacle avoidance phase, the control car needs to keep a safety distance and ensure passengers' comfort. Also, the velocity and the steering angle should be close to the reference with minimum variations. And the variations for the steering angle should not be too aggressive. And if there is conflict among all these criteria, the priority is always given to the computational time. And if the conflict is among the rest of the criteria, the preference is given to the ones that lead to safer driving practice based on calibrators' experience. So here we show the following slides will show the process of the calibration using the preference-based approach. In this case, the maximum number of experiments is set to 50, and these are the parameters in the glyphs operation, and we set with these values. It is tested in the machine and in MATLAB interface. So this is the first comparison that's made. And in this case, we choose the left over the right, even though it seems a little bit better, but we notice that the computational time has exceeded the sampling time. So in this case, we choose the left. For the second comparison, we choose the left over right, because for the right case, the lateral movement is a bit too far. And for the third comparison, we choose the right over the left, since the velocity of the right scenario is better, is less aggressive comparing to the left one. And for comparison number 10, we choose the right one with the same reason as the previous one, the velocity. And for the 20s, we choose the left because lateral movement in this case is less aggressive comparing to the right one. And for the comparison 35, the right one is selected because the computational time of the left one exceeds the sampling time in this case. And for the 38, we choose the left due to the lateral position, less aggressive. And for the 43rd, we select the left one since the steering angle of the right one seems very aggressive. And for the 48, we select the left one since the steering angle of the right one is slightly better, slightly worse than the left one. And for the last comparison, which select the left one, since the computational time of the right one exceeds the sampling time for the left, for the right one. And so, as we noticed, just after 49 comparisons and 50 experiments, we were able to get pretty good results for this test scenario. So in conclusion, preference learning can be a very powerful tool for guiding calibration to optimality based on human assessments. Semi-automatic tuning might be well solved by preference-based learning when these conditions are satisfied. And our current and future activities are denoted to add new features to the calibration algorithm, and also explore the distributed active learning, and also to extend application other than control calibration. And that's all for the talk. And if you have any questions, please let me know.
Okay, thank you for your very interesting presentation. Again, if anybody from the audience has a question, you can write in the chat and you would be allowed to speak. So in the meantime, I have a couple of questions to you. So the first one is probably something that you said or that is specified in the paper that you cited, but what is the idea based on which you select the next value of the parameters after the feedback from the user?
So you mean how to select the next values?
Yeah, you know, the next theta,
yes,
you know, that you then use.
So it's based on the acquisition. So it's an acquisition function. Can you see the slides?
Mm-hmm.
Yeah, so it's like, so it's based on acquisition function, which trades off between exploration and exploration. And for more detail, it's presented in the paper from Bemporad and Piga.
Okay. So it's something that was already available. Okay.
Yes.
Okay. And the second question is more a curiosity. So how do you think that the optimal values of the parameters is dependent on the kind of maneuver that you want to address? You know, so if you, for example, choose another instance of the problem, for example, you are approaching to a traffic light or something like that, do you expect that the optimal parameter value is more or less similar to this one, or it could be in principle very different?
I think it will be a bit different, since like in this approach, we don't really like using a scoring function specifically. We are like case dependent, depends on the case scenario. We select the best action for this case, like and the underlying algorithm is optimized certain functions that in our mind that think for this case, for this test scenario, this action is best. But if it's like a traffic avoidance, it might be like a different scenario. We might have like a different function in our mind that thinks that should operate a bit differently.
Okay, thank you. So I don't think that there are other questions. So thank you again, and we can move on to the third presentation. I don't know if the speaker, Marco Forgione, is already here.
Thanks for your time.
Probably not, because he had another talk. I don't know. Okay, bye, Mengjia.
Right, thanks.
Thank you. So let me see if... No, so the third speaker is not here yet. However, we have another couple of minutes before...
Sorry, I'm Graziana Cavone, and I see that Marco Forgione is writing now in the chat, so I think he's there.
Okay.
Maybe...
Yeah,
sorry. Okay,
so thank you very much.
I'm here. I was presenting on another session.
Okay, yes, I know. Okay, so Marco, if you want, you can start sharing your screen, and we are perfectly on time. So
Just a sec. Okay.
Okay, If you prefer, you can also turn on your webcam if you want, but otherwise it's okay also this way. Okay. Okay, so the next presentation is titled Efficient Calibration of Embedded MPC and will be given by Marco Forgione. Please.
Hello. Hi, everybody, and thanks for following my presentation. So this presentation is strongly related with the previous one. And it's a collaboration I've been doing with Dario Piga from IZIA in Lugano. I'm also in IZIA, and Alberto Bemporad from IMT Institute in Lucca. Cannot turn my slide. Okay, yeah. So motivations of this work. Model predictive control is a powerful and flexible tool to design controllers for physical systems. It can handle nonlinear system, MIMO systems, systems with constraints. And for these reasons, and its flexibility is getting more and more popular. One limitation, however, to the diffusion of MPC is the difficulty in tuning. There are a lot of variables and decisions to be made to set up a working MPC controller, a good one. We have to choose the prediction model, of course, but then the cost function that we optimize online, so its weights and the prediction and control horizons, and so on and so forth. So we recognize that the effort is even more in the case of embedded applications, where because in embedded we may have limited computational power, and then we need to choose carefully also some lower level details of our implementation. So if we have a linear quadratic MPC, we're probably using an optimizer, a quadratic programming solver to get the solution online. But then also the solver has some settings like its tolerances for the solution, and those also have a role in the design of MPC. And more importantly, we have to choose a feasible sampling time, the sampling time such that we are able to compute the solution within one sample time, so we can run it in real time. In this paper, we are proposing an approach to ease the calibration of MPC, and it's based on global optimization. So we perform repeated experiments on the system, guided by a global optimization algorithm, whose role is to maximize performance while keeping a constraint on the sampling time. The sampling time must be larger than the time that we need to compute the solution. This work was also presented at IFAC 2020 in a virtual session, by the way. Anyways, the structure we have in mind is the following rather standard one. We have a physical system S producing an output. We have a state estimator because the output is not the full state. And then MPC controller is designed to track a certain output trajectory, to also receive the state information, and produces the input for the system. So classic feedback control. We have a model of the system that is in continuous time, but it also may have some free parameter, uncertain parameters to be set. Those are tuning parameters for MPC. And then we apply MPC in discrete time. So the discretization time of this model is an important parameter because MPC will run at this rate, and we must be able to do everything, all the computation at this rate. Other important parameters are in the cost function. Here we have just a common quadratic one, but the weights of determine y and delta u in this case are parameters, so as the prediction and control horizons. And so far we have these parameters that we have identified: model parameters, the MPC sampling time, the cost function parameters. Then we may have some lower level parameters that have a role. We are using a quadratic programming solver, and we are setting the solver absolute and relative accuracy as parameters. And this can have an interesting role, because if we lower the tolerances, we may be able to compute the solution faster. and then to close the loop at a higher frequency. On the other hand, the quality of the solution may decrease. So there is this also can have an impact on the performance, and there is an interesting trade-off going on here. And then finally, we have a state estimator. We have a standard Kalman filter, but its covariances are also tuning variables. So in order to run our procedure for MPC calibration, we need to define some things. We need tunable design parameters, and we already have identified them. We collect them in a vector, a design vector theta. Then we need to be able to measure how the performance goes in one experiment, and we define a performance index that is a function of measure the inputs and outputs during an experiment, but it's also indirectly a function of our design choices. And indeed, we want to optimize this J with respect to theta in the end. And then we need to be able to run repeated calibration experiments, or at least relevant simulations for calibration. Because our procedure is the following global optimization problem, where we minimize the performance index. Well, it's a cost, so we minimize it with respect to theta, subject to the constraint that the time we need to compute the solution is less than the sampling time of MPC. And here we stress that we don't know the functional dependency of J and T-calc MPC on theta. This might be very complex, but we assume we are allowed to perform experiments, evaluate point-wise, and so do some calibration experiments. And we use a global optimization algorithm to guide the experiments and hopefully solve this optimization problem in the end after a number of iterations. We could use several derivative-free algorithms to do the job, like response surface, Bayesian optimization, and so on and so forth. But they must be derivative-free algorithms because we measure the value of a function, possibly with some noise, but we have no derivative information. In the work, we are adopting GLIS, that is a recent method developed by one of my co-authors, Bemporad in Lucca. It uses like a response surface method is based on a surrogate function because the function is unknown, is approximated as a surrogate, but it also uses some techniques to promote exploration, and we see something in the next slide. So the goal is to solve a global optimization problem like the following, like the one we have. And initially we know nothing about the function, so we just start collecting random samples. A sample is a tuple with one configuration of all the parameters and the corresponding performance. So we run the experiment and we see the performance. And we do it for a number n of initial experiments. And with that, with this initial data set, we build an initial surrogate. We have an example here on the right. It's an illustration in 1D to be more readable. So the true function, which is unknown, it's this red function. We measure point-wise, and we use a surrogate to use some kind of function that fits this point somehow. Here we in GLIS radial basis function is used. If we were doing just response surface, we would choose the next point to be tested simply by minimizing the surrogate. But this solution typically gets trapped in local minimizers. Maybe we will concentrate all the effort in one region and completely ignore another one, and maybe miss the global minimum. So GLIS explicitly promotes exploration, including the so-called exploration function, the IDW, inverse distance weighting exploration function. It's the exploration function used in GLIS. We have an intuitive representation here on the right. The exploration function is this z of theta in green color, and it takes value 0 at points that we have already observed. There is no point in testing them again, and it takes higher values in between for points that are far from previous observations. And in the end, in GLIS, we don't just optimize the surrogate, we optimize a weighted average, basically, of surrogate and the exploration function. We do this optimization, this mathematical optimization as a software on the PC, and then we have a parameter to be tested in reality. That theta n+1 will be tested, an experiment will be performed with theta n+1, the minimizer of the acquisition function, to get the next point. And then the procedure is iterated. We have a new point, we fit a new surrogate, hopefully more accurate than the previous one, and we have a new acquisition function, and so on and so forth, until we get a satisfactory configuration. So this is applied on a classic benchmark for control systems, the carpole system. Here we have a cart. We want to control its position to follow a trajectory while balancing the small mass. Of course, it's an unstable system, so it's rather challenging. The input is a force F. And but on the force that we added a fast disturbance. We did it because having this fast disturbance makes it convenient to close the loop also fast for to reject it. But still, we cannot reject as fast. We cannot close the loop as fast as we want because we have a constraint on the sampling time. We have to be able to implement online. So here we are optimizing on the sampling time, on the weights of MPC, prediction control horizon, Kalman filter covariances, and solver settings. We're not tuning the model here, but in another example, we will also tune the model. So the codes of this example are all online available. It's 100% open source code. Anyways, we tested it. We tested the same problem on two different hardware platforms to compute the MPC control law. We have an Intel i5 PC, which is kind of powerful on the left, and an ARM, a Raspberry Pi 3 on the right. The Raspberry Pi, we tested it. It's roughly 10 times lower than the PC in the computation of the control law. So we expect the constraint on the sampling time to be more severe on the sampling time because it's a slower device. And this is reflected in the results. On the left, we have the results for the PC, and on the right for the Raspberry Pi, position, angle, and force. We see that the position tracking is smoother on the PC than on the Raspberry Pi, so as the angle is more like moving in a smaller range on the PC than on the Pi. And if we look at the configuration found, we have many parameters, but here we show the sampling time found on the PC was 6 milliseconds, while on the Raspberry Pi it was 22 milliseconds. And 6 milliseconds we tested the configuration on the PC will not be feasible on the Raspberry Pi. In this sense, our algorithm was able to squeeze to obtain the maximum performance that was possible on the two hardware platforms. On the PC, there was more power, so it was used to close the loop faster in this case. We can also take a look at how the cost goes with the iterations. Initially, we have a very high cost, both on the PC and on the Raspberry Pi. This high cost is related to those initial exploratory tests. Then somehow, after about 40 experiments, most of the configuration tested have a kind of a low cost, but still from time to time, there are experiments that are basically failed. But this is normal. This is because GLIS continuously try to balance exploitation and exploration. Even at the infinite, it will still test some points in the parameter space that are far from previous observations and maybe give poor performance. But the idea is to find a good one, and this is okay. This is the expected behavior. And okay. Yeah, this is just another example. It's also possible to tune the model parameters with the same framework. This is kind of interesting, is like doing identification, but not by minimizing a fitting cost, but really by minimizing a quantitative performance index. But it's done in the same way as before. We just change the parameters we tune. And the similar results, that the results we achieve are even better than what we could do by linearizing the true model and then doing some manual tooling. It's kind of interesting, in my opinion. And concluding, we have this approach for embedded MPC calibration based on global optimization and repeated experiments. We can tune altogether high-level parameters like the model or the cost, the weights and prediction control horizon, and lower level settings like the solver tolerances and the sampling time. We tested in simulation on 2 different hardware platforms. There are some extensions to this work. We have some applications in robotics going on. And also we are trying to understand, this is related to a question also in the previous talk, how good is the generalization when the trajectory changes from calibration and after in the final use. So how well the parameters that we learn on one trajectory are for a different trajectory, and whether we can learn a parameterized solution that is valid for a number of trajectories. And this is the end of my talk. If you have questions, you can ask now or
Thank you,
send
Marco.
me an email later.
Thank you, Marco, for your very nice presentation. Now I know one more application from my Raspberries at home. I wouldn't think that I could run MPC on my Raspberry, however. We have a
you can find the software is on my GitHub page, and you can run MPC on your Raspberry Pi.
I will definitely check it. Sure. Okay, so we have a question from Ciro Natale in the chat. Probably.
Hi, I don't know if you can hear me.
Yeah,
I can.
Okay.
So
Hi,
you are
Marco.
here, so you can talk, please.
Oh yes, someone just asked me to switch on the microphone. Okay. Hi, Marco. Thanks for the presentation. I have just a short question. It seems that from the equation of your presentation in part where you show the setup of the global optimization problem,
yes,
that the only parameter subject to constraints is the sampling time.
Yes, it is.
Okay, but don't you think that also other relevant parameters should satisfy some constraints? For example, I don't know, the weight of the quadratic function should be positive semi-definite, or the length of the control horizon should be a positive integer? Or
yeah, this is a good point. Actually, we try to handle those other constraints with a smart parameterization. Like the control horizon is a portion of the prediction horizon bounded between 0 and 1. And yeah, okay. Indeed, the matrices are parameterized in a way to be
matrices,
positive.
Okay, I suspected that you choose a parameterization that ensures you that whatever the optimization algorithm changes the tuning parameters, then you get a positive definite matrix. But then I was wondering about the positive integer of the values of the control horizon length. How do you ensure that it's an integer?
Yeah, that's also a good point. We don't have a way to handle integer values. It's just discretized in this case.
Okay, it's just discretized. I see.
Yeah, it was good enough for this application.
Okay,
but indeed, it's another good point. Thanks, Ciro.
Okay, thanks.
Okay, any other questions from the audience? No, I have just a quick one. I don't know if you have an idea of how the number of iterations or experiments, if you want, scales with the dimension, with the number of parameters that you have to calibrate, or?
Yeah, this is also a very good question. I don't have I cannot tell you if it's linear, quadratic, or I just know that it's used for like 10 to 100 variables, this kind of.
Sorry, for how many
from
variables?
10 up to some dozen of variables. You will not probably handle thousands of variables like this.
And with I don't know, with so in the experiments that you shown, you run 500 iterations, I think.
Yeah, actually
Yeah.
the solution was almost, yeah, it was already after 100 iteration or even 50, 60. It was just to show and then to study.
And the number of parameters was 19, right? The number of parameters.
I think 14 in that
14.
example.
Okay.
Yeah, but that is the kind of
Okay, the
number of
order of
variables.
magnitude. Okay, so thank you very much, Marco. So we can move on with the fourth presentation, which is titled A Robust Scenario MPC Approach for Uncertain Multimodal Obstacles, and will be given by Ivo Batkovic. So Ivo, if you are here, you can, okay, you have already shared your desktop. So if you want, you can start.
All right, great. So can you hear me?
Yeah, we can, okay, we can also see you. Okay, please go ahead.
Great. All right, so thank you for the introduction. Today I'll present a paper we submitted and I got accepted to LCSS and CDC. And this is together with Ugo Rosolia from Caltech, Mario Zanon from IMT in Lucca, and Paolo Falcone, who's at Chalmers and University of Modena. I'm doing my PhD at Chalmers also, and I'm employed by Zenuity, which is a self-driving car company, and I'm partially funded by this Wallenberg Autonomous Systems program. So the motivation behind this talk is coming from the autonomous driving applications. And in such applications, you're typically faced with decision and control problems and road users. So consider this scenario down here. You have a pedestrian that might approach this intersection and this car approaching here.
Sorry, I think that you are seeing this always still the first slide.
Oh, really?
Yeah. At least me, I am just I can see only the first slide.
Let's see. Maybe I restart. Is this better?
Yeah, now I see the second.
Okay, great, thank you. So typically in these self-driving situations, you have pedestrians that might appear and you have cars driving. So if you don't plan ahead what can happen in the future, you might end up in a bad situation like a crash. So what we try to do in our project, or at least in my PhD project, is how to leverage the elements of planning and leverage elements of prediction to get some kind of safety guarantees. But for this talk, I'll focus on the paper. And in this one, we actually discuss on how to handle multimodal uncertainties. And what I mean with this is, consider the following example. You have this car as a human driver, you're approaching the intersection, and depending on what this pedestrian does, you will behave differently, or at least depending on what you believe it will do. So let's say that you believe that the pedestrian will just keep on walking. Then as you approach this intersection, you'll probably be quite confident to drive with higher speed and maybe be a bit more careful to see what this guy is doing. On the other hand, if you believe that the pedestrian will cross your road, then you will be a bit more conservative and you will maybe reduce the speed so that this pedestrian can actually cross the road. Or you can maybe be somewhere in between. You believe that the pedestrian might cross with some probability, beta I for this case, or you might believe that the pedestrian will not cross. So you try to leverage this and you'll be somewhere in between of being conservative or being aggressive. So this is the question then, how do you leverage this kind of thinking in the control problem? And if we go to the problem formulation, it's quite typical. You have these discrete time systems, you have your states X and control U. The goal is to track some kind of a reference. And while doing so, you want to satisfy some constraints. And in this case, we separate constraints to be known constraints, for instance, states and control limits. You don't get to accelerate too much or brake too hard. You don't get to leave the road. And the unknown constraints, which will basically be collision avoidance constraints. You don't want to collide with pedestrians, cyclists, and other cars. So ideally, what you want to do is you want to solve this optimization problem. You basically want to minimize some kind of cost, stay on the road for all future times, while satisfying the system dynamics and the known constraints and the collision avoidance constraints. So the overall idea is to find some kind of controller which is safe. And with safe, we mean then this definition that You have some controller that takes you from point A to point B, and doing so, it will always be sure to satisfy all constraints. So you will never crash while you drive your car. That's the overall idea. But now we're faced with a set of difficulties. The first one is that you don't really know where the road users will be in the future. So how do you make sure that you will never collide with some pedestrian you don't know where he'll go? The second is that typically it's difficult to solve these infinite horizon OCPs, so we need to do some kind of reformulation. And lastly, in this case, we want to optimize our feedback policies, and now these depend on states O and X, which will become difficult. So to address these issues, I'll first go through how to handle the future states of the obstacles. So as I said before, the states are not really known. So what can you actually do? Well, one thing to do is you can assume that you can generate some kind of prediction models. So as you can see in this previous case as well, you have a measurement of a pedestrian, and what you can do is you can assume that you know some kind of underlying dynamical model underneath. And then you can model that, well, I believe that pedestrian might either go straight or turn left. And we assume that this model is given to us, and we can also separate this in different modes. So you can have one mode where the pedestrian turns left, one mode where the pedestrian goes straight. And furthermore, we assume that we know some kind of probability estimate that goes along with this. So let's say that we have some kind of method that gives us, we believe that the pedestrian will turn with a 50% chance to the left, and otherwise it'll keep on going straight. And then we gather these predictions in the sets called O n given k to denote the prediction time n given the time k and I as the mode. And just as a notation, we can group this all together as some kind of big set. So now the question is, well, we have these predictions, we have these sets, and how would you actually use this for the control problem? The simplest way you can do is you can first consider a tube MPC. In that case, you have all of these constraints in different time steps in the prediction horizon, and you just want to satisfy them for all different realizations. Right, this is now quite conservative. You don't really leverage the information you have of a pedestrian turning left for this probability or that probability. You'll always be satisfying these constraints. So the MPC problem looks more or less like this. It's standard. You have the sum over the stage costs, you have the terminal cost over here, you have the initial condition, the system dynamics, the no constraints, for instance, don't accelerate too much, don't brake too hard, and you have the collision avoidance constraint. And here you can see that the collision avoidance needs to be applied for all different modes. And that's what causes the conservatism. Furthermore, in the paper, we show that we have recursive feasibility guarantees, which is given through this set. And I won't go into details today for this talk, but it's using results from a different paper we submitted to Transaction Automatic Control, which is currently under review. So if you're interested in how to get some kind of safety formulation in your MPC problem, recursive feasibility, then please have a look at this paper. So instead, what we can do is, what we propose instead of using the tube MPC approach is that you can leverage these scenarios or these outcomes in your MPC problem instead. So instead of looking at trying to satisfy the constraints for all of the cases all at once for one single trajectory, we propose that you separate the MPC problem in different optimization sequences. So you have, in this case, you have two scenarios. You have one scenario where the pedestrian turns left, one scenario where the pedestrian goes straight, and depending on, and then you also have the probabilities here. So then we split up these scenarios for each MPC problem, and we say that for one scenario, we just optimize over one sequence where the vehicle stops. In the other scenario, we optimize over a sequence where the vehicle doesn't need to stop. And then the key question is, how do you combine these different scenarios and trajectories together? And the answer is that you constrain the control inputs. And now the question is, you can either constrain the control inputs for the entire horizon, and then it basically becomes a robust MPC, or you relax it at some point in time. And what we suggest is that you can only relax it up until the point when you know that there is a mode distinction. So if you consider these predicted sets, you say that you have one mode that is belonging to the red set and one mode that is belonging to the blue set. If these sets never really become disjoint in the future, then given a measurement, you can't always decide if the pedestrian belongs to scenario 1 or scenario 2. But instead, if you have some kind of prediction that goes like this, that you have these sets, which are maybe they have an intersection in the beginning, but then later become disjoint, then you can actually say that given a measurement in either of those sets, I know that the pedestrian belongs in either scenario 1 or 2. So the actual MPC formulation we propose then looks something like this. And it's a little bit different than the tube MPC. So this section here, this is just a standard MPC cost for one scenario. And then what we do is we actually weight the different L scenarios we have with the probabilities we have as well. Furthermore, you can see here that for each scenario, we apply the same initial conditions, the system dynamics, the known constraints, and then we apply the constraint or the collision avoidance constraints for each scenario only. Furthermore, we can see that we have this force of, we constrain the control inputs for the different scenarios to be the same, as long as we know that we can't distinguish the modes anymore or the scenarios. And lastly, we use this safe robust invariant set to ensure in the proofs of the paper that this formulation will be recursively feasible. So what happens actually with this formulation? Well, the first thing is that this part over here with the sum of probabilities, this actually approximates the expected cost of the closed loop. So on average, we expect this formulation to be better than the tube MPC approach. A downside, however, is that since you have an MPC problem now that grows with the number of scenarios, if you have a lot of scenarios, it will be more and more computationally complex to solve this. And you can either try to do some pre-processing to cut down the number of scenarios, which are unlikely. And this is more or less discussed more in the paper, so I won't really go into much detail now. But with this said, with the intuition behind the scenario MPC approach, I'll try to, in the last few slides, show the simulations we have. So imagine again that you have this vehicle that's approaching an intersection, and now suddenly you have a pedestrian that stands in front of you. Let's say that we know that the pedestrian will remain for 6 seconds, but then after the 6th second, it will either disappear with probability 1 minus gamma, or it will stay with probability gamma. And now, basically, if the controller believes that you have two scenarios, one will basically be going forward, and after 6 seconds, it doesn't really believe that the pedestrian will still be there. And the other one, it will basically say that I always believe that the pedestrian will be there. So now, depending on the tuning of gamma between the scenarios, one scenario will be dominant or non-dominant. So in the next slide now, I'll show the closed loop states, which I'll try to explain as well. So the top part is actually the position. The middle part is the graph of the velocity, and the last graph is the acceleration. So for the blue line, which corresponds to gamma equals 0, it basically means that the controller that doesn't believe that the pedestrian will be there after 6 seconds gets all of the weighting and the cost. So you can see that on the blue line, it will be very aggressive up until the 6 second mark. And then afterwards, you can figure out if the pedestrian will be there or not, if you're correct or wrong. So if after 6 seconds, the pedestrian is still there, then you see that the controller will actually make a very hard brake because it approached the intersection quite aggressively. If, on the other hand, the pedestrian was, in fact, removed, then you can see that the controller could actually just keep on driving normally. For the case when you have gamma equals 0.5, that basically means that you try to weight the both scenarios with equal much probability. You can see compared to the blue one that you'll have a bit more conservatism in the solution. And after the 6 second mark, you will see that you'll either need to slow down or accelerate again. And then with the gamma equals 1, you'll have basically the robust approach MPC, which will be conservative all the time and try to slow down very, very smoothly before it reaches the constraint. So furthermore, since we actually approximate the expected cost with this formulation, you can also see that when you compute the expected cost, that the scenario approach is at least as good as the robust approach when it comes to the terms of closed loop cost. So this was for the static example and showing how the actual closed loop behavior changes when you have the different tunings. Now, for a little bit more of a clear example, what the benefit is of this is we're trying to highlight the expected cost. So imagine then a similar example again as in the introduction, that you have a pedestrian that's approaching and it might turn left or keep on going straight. So now you'll still have two scenarios, and the MPC will try to leverage which one is more useful. So for the robust case MPC, you will basically if there's a very small chance that the pedestrian will cross, you will always try to consider this. But scenario MPC will try to leverage this information that I can actually be going very aggressive if beta 1 is small. So what we see here in the expected cost then is the red line is still again the robust MPC. It's performing quite bad. The orange line is our proposed approach with the scenario MPC. And the blue line is a prescient MPC, which basically it knows what the outcome will be beforehand. So this is like the lower bound, the best expected cost we can get in this scenario. So when gamma equals 1, it basically means that the pedestrian will always cross. And in that case, the robust MPC, the prescient MPC, and also the scenario MPC overlap. But as soon as you introduce some kind of probability that the pedestrian won't cross anymore, you can see that the robust cost is still being higher, while the scenario MPC is going down and slowly towards the prescient MPC. So in this case, we can see that formulating the optimization problem or the MPC problem in this way, you can at least gain on average some performance compared to a robust MPC. So yeah, if you're more interested about the details, we have this paper. It's published it's on IEEE already, so you can give it a read. But other than that, I would like to thank you for your attention.
Okay, thank you very much, Io, for your presentation. Again, if there's any question, you can write in the chat. Okay, I have one curiosity, or if you want question, probably. So, as far as I understand, you enforce the constraint that for a given number of time instance, the input signals, the input, the samples of the input sequence are equal for both modes.
Yes.
Yeah. So I was wondering two things. If this number of time instance is fixed, so this n bar, basically n bar ij, if it is fixed in all, or if it is something that changes in time, and how to select this number.
So this, in our formulation, this is not fixed. So imagine that you're approaching, let's say that you first see a pedestrian that's walking along the road. So during your initial planning horizon, you might maybe not see that the pedestrian will reach this intersection, this splitting point. So at that time, it doesn't really make sense to have two different modes because the modes will be the same. Okay. But as the pedestrian is approaching, you basically have this splitting part, this bifurcation part, which will be occurring. Let's see, this one. That's when this constraint is being relaxed. So as you're approaching this more and more, you can basically have more and more leverage on how much you...
So basically you are able to tune automatically this number based on the evolution of the modes that you have in mind.
Yes, that's the idea. And what we present in the paper, at least, that this n bar is selected as the first time these modes become disjoint. So let's assume that the prediction guys give you this, saying that after 5 seconds, we know that mode 1 and mode 2 are separate.
Okay, I see. Thank you. Questions from the audience? No. Okay, so thank you very much again, Ivo, and we can move to the 5th presentation, which will be given by Graziana Cavone. Graziana, you are here, if I remember correctly. You can share your desktop if you want. Okay. Oh. Yeah. I'm still seeing Ivo. Graziana, are you here? The mic. You should unmute the mic, probably.
Okay, can you hear me?
Yeah, now I can hear you. I cannot see you, but I can hear you.
Okay, just a second. Maybe I can switch on the video. Okay, can you see me?
Okay, now I can see you. Okay, so next talk will begin by Graziana, and it is titled Model Predictive Control of HVAC Systems in Smart Buildings and IoT-based Architecture. Please.
Okay, so thank you for your introduction. I'm Graziana Cavone of Polytechnic of Bari in Italy. And so in this presentation, as already said, I will talk about model predictive control for HVAC systems in smart buildings and IoT-based architecture. So in this presentation, I will first introduce the paper motivation and objectives, and then I will go on with the paper contribution and positioning with respect to the literature. I will provide some preliminaries on this topic, and I will show the control algorithm that will be applied to a real case study. And finally, I will provide the conclusions. So let's look now at the paper motivation and objectives. Fundamentally, for the reduction of the global energy use, it is really important to enhance the energy efficiency in HVAC systems that fundamentally are heating, ventilation, and air conditioning systems. In effect, the energy consumption of buildings accounts for around 40% of all energy consumed in advanced countries, and most of this energy is consumed by HVAC systems. Such systems are really important for maintaining acceptable hygrothermal and air quality conditions in building indoor environment. And so HVAC system adjusts the building operations to numerous uncertainties while ensuring that the energy efficiency does not affect the occupants' well-being. So this motivates the effort in designing and developing control techniques for HVAC energy efficiency. So what are the objectives? The objective is to develop a control system that is capable of providing both an appropriate thermal comfort to the user in a building and simultaneously minimize the energy consumption that is, of course, necessary for keeping the comfort of the users. Our approach relies on the use of model predictive control and predict mean vote index. And the approach was applied and tested to a real scenario inside the decision and control laboratory at Polytechnic of Bari. The system and control system was developed in the field of a bigger project that is the UCCSM project that fundamentally aims at developing a platform for monitoring and managing the urban dynamics in metropolitan cities. So it is a urban control center for smart metropolitan cities. Let's move on with the paper contribution and positioning with respect to the literature. So among several promising advanced control system approaches, the model predictive control has gained a special attention since it allows to explicitly account for the minimization of energy consumption while maintaining the thermal comfort criteria. The first applications in general consider the minimization of the energy consumption, so limiting the temperature inside a constrained range. But of course, this does not imply the maximal comfort for the occupiers. So various contributions combine model predictive control and the PMV index. And the PMV index is a nonlinear index that, of course, represent a significant challenge in the context of model predictive control. So there are two main approaches to this challenge and issue. On one hand, a simplified and linearized version of the PMV index, and on the other hand, the use of building software that simulate the dynamical behavior of the building zone and use heuristic solvers to solve the resulting nonlinear optimization problem. So in most works that combine MPC with PMV, the algorithms are generally tested in simulation environments only. So our work with respect to the literature looks at an aligned control algorithm that regulates the indoor thermal comfort of buildings and provides a trade-off between the energy consumption and indoor thermal comfort. And to predict the building energy performance, we use a simplified thermal model, and we apply the model predictive approach in a real application by integrating it in an IoT-based architecture. Some preliminaries fundamentally on the predictive mean vote index. Such an index was developed by Fanger and is largely used for evaluating the thermal comfort. It is an index that has a dimensionless value that can vary between plus and -3, that represent a thermal sensation of very hot, very cold. As you can see, the index is really complex and nonlinear, and it includes a lot of variables that regard, for example, the energy metabolism, the effective mechanical power, the thermal insulation of clothing, and so on. So it is fundamentally really complex. So what we did was to linearize to the PMV index around the 0 PM work point, considering a temperature of 21.4 degrees and the absolute humidity saturation value equal to 10. And as you can see, there is a linearized formulation of the PMV that is really simple. And the coefficients that you see in the formulation, H1 and H2, result from the linearization procedure. I will not provide all the details, but the procedure is quite complex and requires many passages for passing from the nonlinear to the linear formulation. As regards the model predictive control, as probably all of you already knows, it is particularly attractive for the control of buildings because it has the capability to merge the principles of feedback control with numerical optimization. At the basis of MPC, we have three main ingredients that are the model, the predictive optimization problem, and the receding horizon control policy. Furthermore, MPC has the ability to cope with constraints on both control and states, and also with uncertainties that are, for example, external disturbances in the building. And we can also have different type of system architectures, for example, multi-layer, distributed, and so on. Let's move on with the control algorithm. We consider a thermal model for a closed environment, such as a building, of course, and/or a room. This is a complex system that includes various elements. As you know, we have walls, windows, and many other devices included in the system. And the thermal dynamics is influenced by the outside climate and the thermal conditions in the contiguous rooms. So the formulation for calculating the temperature inside of the room or the building is represented in the slide. And so we have the temperature estimated at time K that is calculated from the temperature of the environment measured at time K minus 1, the external measured temperature at time K minus 1, and also the total heat and cool gain due to the HVAC system and the control signal provided to the HVAC system. As a time step, we have delta H, and tau is the constant time of the first order model that we use for the system. The optimization problem consists, of course, in the minimization of various terms. In particular, we have the minimization of the quadratic error of the PMV index with respect to its reference signal, the cost of the energy quadratic error, where we have a reference signal that is equal to 0, and the cost of the control quadratic variation into consecutive steps, because we want to ensure the smoothness of the control action. Such objective function is subject to various constraints that fundamentally regard the PMV index and the projection of the absolute humidity, of course also the thermal and the energy model, and we also impose the comfort range regarding the PMV index. The energy consumption, of course, is proportional to the exchanged E. So for the optimization problem, we consider relaxation of the problem. That includes reformulation of the objective function, because we want to ensure the comfort to the users, also in case of noisy environments where, for example, the PMV value could be higher or lower of predetermined ranges. And so we include this penalty term in the objective function in case of PMV constraints violation, and also 4 constraints that include some slack variables for the PMV constraint relaxation. Let's look at the structure of the IoT-based control system architecture. As you can see, fundamentally in the center of all the structure, we have a gateway that is connected to a network of sensors and actuators that perceive the environmental conditions and of course send measurements to this gateway. We also have the set of HVAC modules, a net of course actuators, and also an API that provides the forecast of weather conditions. We also have an external database that is needed for storing the data and so collect and forward the data from to the field and from to the control unit. We also have a control unit that communicates with the database server where, of course, the MPC algorithm is executed, and also an IP device that acts as an end user interface. So we have a dashboard where the end user can control and monitor the situation in the room or in the building. The case study regards, as I said, a real system. In particular, the proposed MPC approach is applied to an office building located in Bari, in Italy. So it is a research center in Polytechnic of Bari that belongs to the Department of Electrical and Information Engineering. And some rooms of this building, where of course the decision and control laboratory is located, have been equipped with a network of sensors and actuators to regulate the occupants' comfort. In the slide, you can see both a picture of one of the rooms of the lab and also the positioning of the devices inside of the room. As you can see, we have the gateway, the multi-sensors, multimeter, occupancy sensors, fan coil unit, controller, and dashboard. So this is the system setup and architecture. We have on the left a dashboard that is based on Node-RED, developed to provide the occupants with the monitoring and control panels. We have the weather forecast from a digital weather information provider through the use of an API. Then we have a multi-protocol gateway that is named Beta Box that collects the data from all the sensors installed in the room and sends them to the cloud platform that communicates with the actuators. And all these data are accessed by the MPC algorithm that is developed in MATLAB on a PC and works on a control station. These are the results. In particular, we consider a midweek day in February 2019. The sample time is set to 2 minutes, while the prediction and the control horizon are both set to 3 hours. So the comfort range for the PMV indicator is set to -0.5 to 0.5. As you remember, I said before that it is an index with no particular indication of the measurement, and just an information about the feelings of hotness or warm. So the MPC approach is limited to working hours from 9 a.m. to 16 p.m. in working days. As you can see from the pictures, the fan speed in the left bottom is increased sufficiently before the beginning of the working period. So the working period, as I said, is 9 to 16 p.m. And so we have the fan speed that is already active before 9. And we consider and estimate the actual number of occupants in the room, and we consider this as a modeling error in the MPC. As regards the performance comparison over all the testing period, for the starter thermal comfort control system, we consider a performance assessment from mid-November 2017 to mid-March 2018, and we have a set point equal to 22 degrees during the office working hour. While for the MPC, we consider a period from mid-November 2018 to mid-March 2019. As you can see in the table, we consider as performance indicators the comfort satisfaction during the working time and the average daily energy consumption. In both cases, we have that the MPC approach outperforms the programmable thermostat approach. In effect, we have an increase of the comfort satisfaction of 20%, more or less, and a reduction of the energy consumption of almost 90%. The PMV, of course, in this case is used as control variable instead of the temperature, and the energy saving term is included in the cost function. So concluding, what we can see is that the contribution of our work is the definition of an MPC algorithm to optimally regulate the indoor thermal comfort. We use the energy cost and PMV indicator in the objective function, and we preserve the indoor comfort to be in a given range in spite of the presence of multiple disturbances. In future work, we will consider to assess the computational complexity and scalability of the algorithm, to enhance the algorithm with a more accurate root thermal model and forecast the occupancy profile, as well implementing more general building models and evaluate the use of robust MPC approaches. So this is all for my presentation. Thank you for your attention.
Thank you very much for your very interesting talk. If there's any question from the audience, you can write in the chat. Otherwise, I have some curiosity about the results that you have shown. So in your experiments, how many, I would say, rooms or modules, I don't know how to say it, HVAC modules are you considering? So how big is the building,
Okay, so this is, of course, a good question. In this case, in particular, the test case, we are now considering the results regarding one room of the building because it was, of course, easier for us to install all the devices necessary for the control system. It was a little bit more hard to install all around the building. So the results refer in particular to the room that I was showing in the very beginning. So as you can see, we have 3 fan coil units that fundamentally regard the HVAC system and only one gateway, various sensors in the network that also regard, for example, the occupancy of the room or the temperature, also the level of oxygen inside the room, and finally the dashboard that is useful to interact with the system.
Okay, and what about the scalability? So if you would install this system in multiple rooms, you have to equip all the rooms with all these units, or just you can use just some sensors and HVAC systems, for example, and you can get rid of other devices?
Okay, fundamentally, the scalability is quite simple because we just need to install all the devices regarding the sensors and actuators in the various rooms and make them connect to the gateway that fundamentally communicates with our server and collects all the data in our PC that is dedicated to the storage of the information and data.
Okay, thank you very much. And I think there's no question from the audience. Okay, so thank you again. We can move with the last presentation that will be given by Renato Quartullo. Renato, if you are here, you can share your desktop.
Yes. Can you hear me?
Yeah, I can hear you. If you could increase a little bit the volume, it would be better, I think. Sorry, there's a question from Gianni Bianchini. If Graziana is still here, we can accept a question from Gianni. Gianni, if you want to talk, please.
Graziana, you still here?
Yeah, I'm here.
Just a very quick question. How do you tune the relative weight in the cost function of performance and constraint violation penalty for this specific problem?
Yeah, that's a really good question. Of course, in general, it depends on how, or fundamentally what you want to prefer. I mean, in the objective function, we have both the energy consumption, the PMV index, so the comfort of people inside of the building, and also the violation of the PMV. So in our case, we consider to give fundamentally the same weight to all of these terms, but in general, I think it is more related to the type of politics that you want to apply to your building. It's quite more related to the owner of the system, and then you can change. So it's not related to a particular formulation or assessment, but you can choose it depending on your own objectives.
Mm-hmm. Okay, that's it. Thank you.
You're welcome.
Okay, thank you. So, Renato,
Yes.
You can share your desktop. Yeah, that's good. Okay, so the next and last presentation of the session will be given by Renato Quartullo, and it is titled An MPC Strategy for Low Thrust Space Debris Rendezvous.
Okay, thank you and good morning. My name is Renato Quartullo and I'm gonna present you our work entitled An MPC Strategy for Low Thrust Debris Rendezvous. Active space debris removal is an interesting topic of nowadays space application because around our planet an impressive quantity of space junk is orbiting. With the term space debris, we indicate discarded rockets, old satellites, and old bodies that make the collision probability in the space grow. Clearly, major space agencies are worried about this scenario. In fact, there is a rich literature on these missions based on chemical propulsion. The objective of our work is to design and implement suitable control laws for such mission, and furthermore to validate the usage of electric propulsion technology for this kind of mission. Electric propulsion could be an important technology to exploit for these missions because this mission requires large velocity changes, and electric propulsion having a higher fuel efficiency with respect to the chemical propulsion will permit to reduce the propellant consumption and then to capture multiple objects in the same mission. Despite its efficiency, electric propulsion arises essentially two challenges, and so it is characterized by a low thrust, and this leads clearly to a limited control authority, and by the fact that it provides an on-off control input, so electric propulsion is essentially binary. In order to accomplish our objective, we have designed a mission of space debris removal that involves the usage of electric propulsion, and we're supposed to use a small CubeSat with one Hall effect thruster, which is the electric thruster on board, and 24 cold gas thrusters, which are capable to exert chemical thrust in each direction. As you can see, the specific impulse of the head is much higher than that of the CGP, but the deliverable thrust is 10 times less than CGP. The mission has been split into 4 stages. The mission starts with the satellite, which is left on the parking orbit by the rocket, and its first scope is to reach an orbit with the same orientation and a lower altitude than that of the debris, called phasing orbit. Once reached this orbit, the satellite must approach an holding point, which is a point situated a few kilometers ahead the debris, and this is done in the phasing stage. Then, with the terminal rendezvous, starting from this holding point, the objective is to reach the capture point, from which the satellite will launch the capture device in order to catch the debris. At the end, the satellite will take the object into a sufficiently low orbit in order to make the atmospheric drag burn. To describe the relative motion dynamics of the two satellites, we adopt this innovative parameterization, which is obtained from a suitable combination of orbit shape parameters, such as semi-axis and eccentricity, and they compare in the second variable, and x3 and x4. The inclination, which compare in variable x5 and x6, and the four angles that describe the satellite position instantaneously, clearly, with respect to the line of nodes. This new parameterization avoids the singularity that other parameterization that we find in literature presents for circular orbits, which are of our interest. So, differentiating this parameter vector, we obtain the relative motion error dynamic model, which is clearly nonlinear. So, linearizing the model around the target orbit, we obtain the state space dynamic in the equation 1. The orbit transfer is referred to the orbit acquisition and the orbiting stage. So the objective is to steer the satellite orbit towards the phasing 1. This means to steer the variable x2, x3 to x6 to 0. The variable x1 is just the phase error of the two satellites, so it is left uncontrolled in this stage, but it will be controlled in the next stage. Being this stage the longest one of the mission, we want to use only the hat in order to save the fuel. So for orbit transfer, the control law shown in the slide guarantees the practical stability of the error system, also guaranteeing the binary nature of the electric propulsion, thanks to the normalization term that you can see in the equation. As you can see, this law is simply a discontinuous version of the classical damping control law. For orbital rendezvous, a discretization of the linearized system is needed. Then we will understand the reason. This time, also variable x1 is considered, because now the objective is to guide the satellite toward the holding point or the capture point, which have a certain phase error specified. So the orbital rendezvous is referred to both the phasing and the terminal rendezvous stages. And in these steps, together with fuel reduction, there are also safety and trust requirements to be satisfied. In particular, the trust constraints are essentially two. The first one is that the altitude of the satellite is supposed to be fixed and aligned with the body frame, so that the total thrust is just given by the sum of the two propulsion systems. Here, the variable s is just -1 or +1, accordingly to the orientation of the satellite with respect to the orbit rotation sense. In particular, in the phasing stage, the satellite will move in the same sense of the orbit, while in the terminal rendezvous, it will be the direction will be the opposite of the orbital sense, so s will be -1. The second constraints are due to the nature of the thrust systems. If you remind the CGT's configuration, it's easy to claim that the thrust of CGT can be represented by a limited box identified by the infinity norm. Instead, the head command is forced to assume just two values, 0 or the maximum deliverable thrust. This is This is done to meet the binary nature of the electric propulsion. The second important requirement is to carry the mission in a safe manner, in the sense that collision with the same debris must be avoided, and also to make the target fall in the visibility cone of the optical sensor of the satellite. This is modeled, this constraint is modeled by an hyperplane that you can see in the slide. This hyperplane in the state space that describe the forbidden region for the satellite. So setting the constants C1, C2, and D, you can regulate this hyperplane in order to meet optical sensor requirements and safety requirements. Now, since the control problem imposes several constraints and it is aimed at reaching some important points, while minimizing the fuel consumption, the most suitable control approach may be the model predictive control, where the cost function to be minimized weights a state regulation performance term through the matrix Q and the fuel consumption. Notice that the ratio of the two specific inputs that weights the head command is much lower than 1. So merging all these constraints that I mentioned before, we get into the MPC formulation that you can see in the slide, in which this control at each step, at each time instant, this MPC scheme must be solved. And clearly, at each time instance, only the first input of the optimal control sequence must be applied to the system. Here, N is the horizon, is the prediction horizon. Now, as you can see, the optimization problem shown before is cast as a mixed integer linear programming with N, where N is the time horizon, binary variables. Clearly, the larger is N and the higher is the computational burden. Now, for the terminal rendezvous, being the distance between the two satellites very, very small, N could be small. So for rendezvous, for terminal rendezvous, the MILP problem can be solved. While for the phasing stage, N must be very large to retain the MPC feasibility. So we need a relaxation. So our idea is to relax the input constraints on the head command in the classical way. In this way, the MPC optimization simply become a linear programming problem, clearly with a computational burden less. And as you can see, then once applied, once solved the MPC scheme, an heuristic is applied to the command, and using this actuation scheme that you can see in the slide, the relaxation of the constraints, as you can see, is based on the structure of the tasking systems, and it is not the classical approximation to the nearest integer. Another important fact to be noticed is that this solution is optimal also for the original MILP problem. Okay, in order to validate such control schemes, a rendezvous case study has been implemented and simulated. We suppose to start with an initial intersatellite separation of about 500 kilometers, and we want to reach the holding point, which is located 2 kilometers ahead of the debris. The resolution of each instance required in average 1 second, which is a time much lower than the sampling time, that is about 3 minutes. And you can see in the figure that the satellite reached correctly the holding point using mostly the head propulsion. This is done because clearly the solver prefer to use the head command. Okay, after the phasing, the terminal rendezvous stage can start. Also here, you can notice that the satellite reaches the capture point, which is located more than 1 meter ahead, 1.5. And also here, this is done by using most of the time the head command. Also here, the computational time is less than 1 second, so it is in the time interval. And as you can see, being n very small, the MILP solution has been possible. Okay, now in order to validate also the mission design and the electric propulsion usage, an entire mission in which the satellites must capture 2 debris located in different orbits clearly has been simulated. The mission lasts 250 days with a fuel consumption of about 25 kilograms. And consider that typical small cube SAT brings a tank of 35 kilograms of propellant. So basing on this data, one satellite can remove about 3 debris in about 1 year in one single mission. And this is thanks to electric propulsion. So in conclusion, in this work, space debris removal mission has been designed and simulated. And in particular, the orbital rendezvous stages for which an MPC scheme has been worked out, since MPC approach has been identified as the most suitable control technique. Finally, also the validity of electric propulsion for this mission has been devised basing on the data that I showed you before. Thank you for attention.
Okay, thank you, Renato, for your talk. Now we are waiting for questions from the audience. This time I don't have curiosities or questions because I am one of the co-authors, so I'm just waiting for questions from you. Okay, so if there are no questions, I think we can finish our session here. So we have seen many applications and we have seen many aspects of MPC studied in this session. In my opinion, it was a very interesting session from the technical point of view. And I hope you enjoyed it. And now I think it's time to have lunch. And I hope you will enjoy the rest of Automatica.IT. Okay, thank you everybody for your time, and see you in the next on the next beaches. Unfortunately, only virtual beaches. Okay, bye.